Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the final video in a series on vectors, an introduction to vectors for trig and pre-calculus students. You should already be familiar enough through this video series with vectors, how to add, subtract them, all that fun stuff. And this video is purely dedicated to applications involving vectors. They're really fun to deal with. The first thing we need to start with is just what is force. A force is a push or a pull, and you probably know a very famous formula. Force is mass times acceleration. If you don't know that, it is true. Force is mass times acceleration. And that will be very useful in physics and incredibly useful in differential equations. It won't be super useful here. Now, in the United States, we generally measure force in pounds. Although it doesn't necessarily have to be measured in pounds. It is measured in pounds in the United States, and I think Burma and Libya as well. And then everywhere else, they measure force in something else, and that is called a Newton. And we're not going to deal with that also as well in this video. We're going to keep in pounds and stuff like that. But anyhow, by the way, little side note, when you weigh yourself on a scale, you're weighing the force, you're weighing how much force you're exerting on that scale, and it's dependent upon where you are. So your the force you exert on that scale would be different if you were standing on the moon. However, some scales give give a weight in kilograms, and that's a lie because that's a mass, and there's no scale. Well, your household scale does not or should not measure mass, but it's calibrated for basically sea level, so that's why they can get away with that. That's a little side note. Anyway, a man pushes a lawnmower with a force of 40 pounds, exerted at an angle of 45 degrees to the ground. Find the horizontal and vertical components of the force. Now, this is just something that I need to remind you of. We've been dealing with vectors, and vectors have a direction and a magnitude, and that's exactly what force is. Force has a direction. In fact, a person pushing a lawnmower like this would be pushing, let's say I said 45 degrees downward, right? So they would be pushing with a vector that looks like this. That is their force vector. I'll call that capital F with a little vector symbol over it. That's their force vector that they're using to push the lawnmower. There's a vertical component to that force vector and a horizontal component to that force vector. And so obviously the vertical component kind of gets wasted because you're not pushing your lawnmower into the earth. You shouldn't. You should be pushing, honestly, this direction to minimize the amount of force you have to push with, to be honest with you. But most people do push slightly downward, mainly because they probably don't want the back wheels to kick up or something like that. So the question here is really a vector question. If we know that this force vector is at an angle of 45 degrees to the ground, so if this were the ground right here, this would be a 45 degree angle. That is, this angle is 45 degrees because they're alternate interior angles. Then the question is, what are the components of the force? And we happen to know from the previous video that a vector V with components A and B satisfies the following. A is equal to the magnitude of V times the cosine of the angle that the vector V makes, and B is the magnitude of the vector V times the sine, the angle the vector the sign of the angle that the vector makes with the positive x-axis. And so, by the way, that would be this positive angle with the x-axis. Now, I did not tell you which direction this person was pushing the lawnmower, so that is slightly weird in this situation, but let's just go ahead and pretend it's this direction. All right, so if that's the case, this vector has an angle of, let's see, 90, 180, 270, plus an additional 45. 270 plus additional 45 is 315 degrees. So right now, I happen to know the A component, or the horizontal component, that's what A is the horizontal component of the vector, is going to be the magnitude of the vector times the cosine of 315 degrees. And the vertical component is going to be the magnitude of the vector times the sine of the angle 315 degrees. Now you can compute those pretty quickly. They both have reference angles of 45 degrees, and cosine in quadrant 4 with a reference angle of 45 degrees is 1 over root 2. So at this point, I sort of speed through my trig, mainly because you guys should all be very experienced with trig at this point. The sine of 45 degrees is also 1 over root 2. However, it's in quadrant 4, so it's a negative. So we have the magnitude of v times a negative 1 over root 2. And finally, the magnitude of our vector. And I called it v this entire time, so I'll call this v as well. So I already have that little arrow over it. And we are told the magnitude of that force vector was 40 pounds. So that'll be 40 over root 2 for the horizontal component, and a negative 40 over root 2 for the vertical component. So those are the horizontal and vertical components of the force. And by the way, their units are in pounds. So this is how many pounds the person is pushing into the ground. Wait, is that A? No, that's how many pounds the person is pushing horizontally. And B is how many pounds the person is wasting by pushing into the ground. Wasted energy is what that is. You can also use vectors for moving objects like this. So I'm going to read it out loud, and then we're going to draw it and do all that fun stuff, but then I'll tell you other styles of this problem. So a river flows due south at 5 miles per hour. So I'm just going to draw in a river here. So here's our river. It's flowing south at 5 miles per hour. In fact, notice how I just did that. I drew a little vector there. So this is a vector aiming south, and it has a, I'm going to call this the river vector. And we know that the magnitude of that river vector is 5. So that's because it's 5 miles an hour south. So that's the length of that vector. There's a swimmer attempting to cross the river, and they're heading due west. So the swimmer jumps in the river right here. They're heading due west. And notice again, I drew an arrow there because it's very natural to do that. And they're swimming at 3 miles an hour. So the size of that vector should be shorter than the size of our R vector. So I'll just write it this way. Here's our swimmer vector. And the size of the swimmer vector should be 3. The question is, find the true velocity of the swimmer as a vector. Okay, well, what does that mean? It means this. You have a vector called the swimmer, and they're trying to go this way, but the fact is the river is pushing them down. So their true direction and their true velocity is adjusted. It is going to be whatever their vector is, this S vector, plus the river vector. So let me grab the river vector here. Oh, whoops, that was supposed to be me grabbing the river vector, but it didn't quite work out. So plus this river vector right here. So the sum of those two vectors will actually be the resultant vector, which is the true velocity and what we would call the resultant vector. So that is how you could use vectors to showcase where things end up if there's wind acting on an object or something like that. So in this case, you have a swimmer trying to go this way, but the river is pushing them that way. So what is their actual direction and what's their actual speed? Well, that's actually not too terrible to figure out here because these two vectors are perpendicular to one another. It's a right angle. They told me that the swimmer is swimming at a magnitude of 3 and the river is moving at 5. So I could find easily the length of this resultant vector right here using the Pythagorean theorem. Right? So we have 3 and 5. This will be the square root of 25 plus 9, which is 34. So that is the resultant speed of this swimmer. And let's go ahead and figure out the resultant direction too. I kind of want to know that. So let's do that. By the way, that square root of 34 is roughly 5.83, and that's in miles per hour. So that means that this swimmer who was trying to go 3 miles per hour across, they're getting pushed by 5 miles per hour south. And combine that with their current speed, they're moving a little bit faster than that. They're moving at 0.83 miles per hour, but in the wrong direction, right? Totally not moving west. They're moving southwest. Let's see through what angle here. So to find the angle, you can go ahead and just draw this picture right here. You have a theta right there, and you can find that angle just easily by using like a tan inverse. So theta hat technically is tangent inverse of 5/3, and that is approximately 59 degrees. So they're 59 degrees off course. Now I should probably go back to the problem to figure out what they were asking. So find the true velocity of the swimmer as a vector. Okay, so the true velocity vector is going to be let's see, -3, -5, because again, they're going over 3, but down 5. And so that would be their true velocity as a vector. But again, I like my answer a little bit better. It showcases how fast they're really going because you found the hypotenuse of that triangle, and it showcases how off they are as far as their angle. These are very, very common. Another common style for this is if you're on a boat, right? So let's say you're on this boat right here, you're standing right here, and the boat is moving this way at, let's use the same numbers, 5 miles per hour. And you start walking this direction at 3 miles per hour. Then what is your resultant vector, or what's your resultant direction and speed? It's the same style of question. You have one vector pushing you this way at 5, and you have another vector pushing you this way at 3. Your resultant vector is your true speed and your true course. Another situation is if you're in a plane, right? And a plane has an intended heading this way. Let's just pretend. So that's our plane's intended direction and magnitude or speed. But maybe there's a crosswind. And so the crosswind might be this direction and a really strong crosswind, maybe that type of magnitude. What is the resultant direction of the plane and what is their resultant speed? Well, that would be the vector that connects the initial point of P to the terminal point of W. That would be this vector right here. And actually, that's one of the examples we have coming up. But this is a really great use of vectors. And all it is vector addition the entire time. So let's go ahead and do that airspeed one. A jet is flying through a wind that is blowing with a speed of 55 miles per hour in the direction of north by 35 degrees east. So let me showcase what that is. First of all, if you know that from heading problems, because we've done heading problems before, whenever you face a heading problem, you want to draw in kind of a target here, the north, south, east, west target. And then they tell us that this vector is face north and turn 35 degrees east. So 35, that'd give me a 55 degree angle here. So I'm just going to do that. And they tell me this vector has length 55 because it's a 55 mile per hour wind. So there we go. We'll just pretend as though that's 55. Actually, let me measure it out. Well, I don't think it's going to be very easy to justify. So I'll say that that's our wind vector right there. Remember, this is a 35 degree angle right here, north by 35 degrees east. And then the jet, on the other hand, has a relative speed, or an intended speed, of 720 miles per hour. And the pilot has the intended path of north by 15 degrees west. So let me showcase that. Again, that pilot has a heading of north. So notice how I'm doing my crosshatch here just to showcase this. North by 15 degrees. So that would mean 90 minus 15 is 65. So something like this. Now I'm going to run into that picture over there. So let me move this. Do this. Actually, I'm going to move this picture over here. Get it away from me. And I'll move this guy over here. All right. And north by 15 degrees, it's going to be that. And the intended speed was super huge. Okay. So this is the intended speed. But that angle is 15 degrees because it's north by 15 degrees west. So there's our vector representation of this situation. And what do they say? Find the true velocity and the true direction of the jet. Okay, let's do that. We know the length of this vector for the jet. I'll call this capital J with a vector symbol above it. We know the length of that is going to be 720. So obviously this is not drawn to scale. And the length of the wind vector is going to be 55. Again, totally not drawn to scale. And as you recall from our earlier videos on applications involving heading and bearing and stuff like that, you want to connect these up just like this. This is actually very similar to those problems when somebody goes hiking or something and they go so many degrees this way and that way, and right? It's the same style of problem, but we really want to know what's the resultant vector, what's the resultant distance here, and what is the resultant direction. So I'm going to draw a line connecting the initial point and terminal point of these right here. It probably won't be too exact, but there you go. And remember, this is not drawn to scale, so don't expect my answer to look anything like what this is, but there we have it. All right, so we want to know let me label some things in. This will be our true vector. We want the size of that true vector because that would be their true speed. We also want the angle that is going on right down here. So they were supposed to be going north by 15 degrees west. What is it now after that wind? And this requires us to just kind of redraw a little bit. First, before redrawing, I'm going to label a few things. This angle is 15 degrees. Its alternate interior angle, which is right here, is also 15 degrees. So because this is a right angle there, we know that this must be 90 minus 15, which is 75 degrees. All right. And let's see, what else do we need? Oh, I must have measured that angle incorrectly before. Sorry about that. Anyhow, we know that this is 35 degrees here. And because this is a right angle, 90 minus 35 is 55 degrees. And notice we have one angle of this triangle and two sides of this triangle. I could use the law of cosines to find this missing side because I have a missing side, but I have the angle opposite it. So I can use the law of cosines here. And if you need to, you could label things because that's how I teach my students to do this. So let's go ahead and just quickly sketch out a picture that is probably highly inaccurate. Let's see, 55 plus 75 is 120, 130 degrees. So let's just call this 130 degrees. Let's call this angle little t because I called this side big T. And Let's call this angle way down here little w, because I called the opposite side big W. And let's call this angle up here little j, because its opposite side was big J. And now I make my table of values. Let's list the angles. So J, T, and W. We don't know J. We do know T is 130 degrees. We don't know W. Let's see. And let's list out the corresponding sides. Let me loop this up because I need a little bit more room here. Let's see. Side J, we know that's the jet speed 720. Side T is what we want to find out. We don't know that. And then side W is the wind speed, and we know that's 55. Notice we do not have a complete row, so law of cosines is the way to go here. So law of cosines. So let's see. Side T squared would be side J squared, 720 squared, plus side W squared, 55 squared, minus twice side J times side W, cosine of the angle opposite side T, which is 130 degrees. And then you take the square root of both sides and grab a calculator. So that's what I'm going to do right now. Grab a calculator and figure out what this is. And I get 756.5. Let's just say, let's round to the nearest decimal place. So 756.5. Now remember, this is a speed in miles per hour. So they intended to go 720, but because of the fact that they have this crosswind, they gain a little speed. So you have 756.5 miles per hour. Now we want to know how far off course they are. Their intended course was north by 15 degrees west. That's this one right here. We would love to know what the true course is. So let's go ahead and find out what this little sliver of an angle right here is. And that is angle in our triangle. That's angle W right here. So I'm going to go ahead and just fill this in. This is roughly 756.5. And I'm now going to use this full complete row to find out what W is. And I can use the law of sines here because I know the obtuse angle is already taken, so I will not have an ambiguous case. So let's go ahead and use the law of sines. The law of sines tells us that W is to the sine, that's angle W, right? So the sine of angle W is to its opposite side as the sine of 130 degrees is to its opposite side. And just to let you know, I have that number saved, 756.5. I have the decimal expansion of that number saved because I don't want to use this rounded value in this computation, and nor should you. But the angle W is going to be the sine inverse of 55 sine of 130 degrees divided by that saved value. Again, I would not use 756.5. I would use my saved value. So let's go ahead and figure out what this is approximately. Okay, I get 3.2 degrees. So we know that this little sliver of an angle is 3.2 degrees. So remember, they were going north by 15, but now they've been pushed off course slightly. 15 minus 3.2 is actually what their true course is. So their course is north by, what is that? 11.8 degrees west. That's 15 minus 3.2. That's their true course. These are really, really cool problems. And notice they do use the law of cosines. You'll use the law of cosines and law of sines quite a bit. That's why this is in trig material. Really good stuff. I totally dig vectors. Now, the last problem that I have here is a static equilibrium problem. And static equilibrium problems are kind of a favorite of mine as well. I really like static equilibrium problems. How they work in general is that you have some object in space. So ignore the wording up above. Let's just start with a kind of an idea. You have an object in space, and this object has a lot of forces acting on it. Let's say that it has a force like this. It has this force right here acting on it, pulling it in that direction with that amount of force. So that might be like 12 pounds of force pulling in that direction. But then it has a totally different force acting upon it. Maybe somebody else is pulling it this way with a slightly longer. Let's do a slightly longer. And let's say that somebody else comes in and they're pulling it this way with that force. And let's say that there's one final force here that's pulling it directly downward. And you could probably guess what force that is, but if you can't, I'll tell you, it's its weight. The planet is pulling it down because that's the force due to the acceleration due to gravity. It's mass times acceleration. So those are maybe all the forces. Like somebody in blue is pulling in one direction, somebody in red is pulling in another direction, somebody in green is pulling in another direction, and that object has a weight so that the Earth is pulling it down. How do you find out what the resultant force is? Because there's a single resultant force. You can figure out which way this particle is going to move based upon the resultant vector. And this was what we did on day one. When I say day one, really it was video one here. But this is what we did with video one, is we took a bunch of vectors and added them up and said, oh, by the way, when you add these up, you get this result. That's what a resultant vector is the sum of all these vectors. So I'm going to take this vector right here. I'm going to move it here. So I'm adding the black vector to the blue vector. And then I'll add to that, maybe I'll do the red vector. I'll add to that the red vector. And then I'll add to that the green vector. So the sum of all of those vectors, by the way, you can do this in any order you want. The sum will always be the same, okay? The sum of all that results in the following. And I'll use orange for this. It results in this following vector right here. That is the resultant vector. So with all of those forces acting on this object, the object's tendency would be to move in this direction with this amount of force. So that is because, think about it, the red and green vectors are both pulling it to the left. That teeny little blue vector is the only one that's keeping it from moving all the way to the left. It's trying to move it to the right a little bit, so it's slowing it down. But in the end, the force of gravity is going to win, and these other two vectors that are pulling it to the left are going to win. So it's going to fall in that direction. If you don't want it to fall, you've got to adjust the forces. Well, the force of weight you can't adjust, but maybe you can adjust the way somebody's pulling in a direction. If you pull to where all the forces sum back to the beginning, that is called static equilibrium. That means that object is not going to move. And that's how you get things like, hanging signs and stuff like that from falling, is that they're in static equilibrium. Their weight vector is offset by the tensions on the cables that are holding them. So let's go ahead and do a problem involving static equilibrium just to showcase how they're done. They're very fun problems. And the way that I do them is pretty standard. It's always the same. So let's read the problem now. A mass weighing 18,278 pounds is attached to a cable that spans a chasm. The angle of depression from one cliff to the cable is 22.3 degrees, and the angle of depression to the cable from the other cliff is 41.5 degrees. The cliffs are at the same height. Find the tensions on both sides of the cables. Okay, there's a lot to read. But basically, you have two cliffs at the same height. I'll draw those in here. You have a cliff here, and at the same height, a cliff here. Okay. You have a cable, they should be the same height, but it doesn't look like they are. You have a cable that, moving that down slightly, that is connected to both sides of this chasm. Let's just say that the cable is connected here and here. Okay. And somebody's standing at one spot right here, and they look down, they see that the angle of depression that the cable makes with the horizontal is 22.3 degrees. So I'm going to go ahead and make an angle of 22 degrees here. So there we go. We have an angle of 22. And I'm just going to draw this cable in. We'll find out where they intersect. So I'm just going to do it like this for now. All right. The other cable, maybe I'll do it like that just in case. The other cable, so somebody else is on the other side. Boop, 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 boop. And they notice the angle of depression to the cable on this side is 41.5 degrees. So let's go ahead and just put it at 41. Yikes, it's fairly steep. So obviously this object's barely hanging on. Okay. All right. I guess I could have drawn that solid, right? All the way up to there. Okay. So let's go ahead and remove that ruler, erase some stuff here, zoom in, maybe erase this and then connect them. There we go. So you have some object right here that's connected. Now remember, this is a 41.5 degree angle, and the other side is a 22.3 degree angle. Okay, so the only forces that are acting on this mass are going to be the force of gravity, which is super huge here because it's a super heavy object. So I'm just going to call it G for the gravitational force. And then the two tension vectors. So you'll have a cable tension pulling it this way, which is not really thick enough, but here we go. So you have a tension vector going this way. I'll call it T sub 2. And you have a tension vector going this way I'll call that T sub 1. There we go. These are vectors. All right. In the end, you want this to be in static equilibrium. If this object is not falling, then it is in static equilibrium. That's critical to note, that this should all sum to 0. Okay. So that's how static equilibrium problems are done, is that you know that these vectors should add to 0. That when you draw them out, when I actually sit here and I go, okay, well, I'm going to draw the gravity vector. Here it is right there. And then I draw the T sub 2 vector. I always do it this way, by the way. When I redraw this, I do the vertical vector first. That's the gravity vector. And then I just have a habit of drawing to the right. So I'm going to grab the vector that moves to the right. So that's my tension 2 vector. This guy right here. Tension 2 vector. And then I will draw the tension 1 vector. Now note, the way that I'm drawing this is not to scale at all. Okay. But what I want to be true is that they meet up where they began. They began right here. So I need them to loop back to meet up where they began. Okay. And now I will go ahead and label the angles. Well, let's see. Tension 1 is going to make this angle of 22.3 degrees with the horizontal. So tension 1 makes an angle of 22.3 degrees, which means this interior angle is 90 minus that. And so if you do 90 minus the, 22.3, you get 67.6 degrees. Oops, 67.7 I meant. Degrees. And let's see if we have anything else that we can use here. Did they give us any other information about angles? Yes, they did. The tension 2 vector makes an angle of 41.5 degrees with the horizontal. So I'm going to go to the tension 2 vector and I'm going to draw a horizontal. And I'm going to say this is 41.5 degrees, which means the remaining part of this 90 degree angle is 90 minus the 41.5 degrees, which is going to be 48.5 degrees. Okay, so far so good, I hope. Now we still have room for an angle, but I'm not, actually, we do need that extra angle. No, we don't need the extra angle. We're good. All right, what else have we been given? Oh, we've been given the magnitude of the gravity vector. The magnitude of the gravity vector is 18,278. 18,278. That's in pounds. And the question is, find the tensions on both sides of the cable. In other words, I need to find out what's the magnitude of this tension and what's the magnitude of that tension. All right, so let's go ahead and make a table of values. I will call this angle A, angle B, angle C. Why not? So angle A is 67.7 degrees. Angle B is 48.5 degrees. Angle C is actually pretty easy to get because it's just 180 minus those. You only have 180 degrees in an entire circle. So let's go ahead and quickly do that. That's 63.8 degrees. So that's kind of nice. And then let's see, side opposite A is tension 2. Which we don't have. Side opposite B is tension 1, which again we don't have. But side opposite C is the gravitational. It's basically the weight of this object, 18,278. Now I can go ahead and use the law of sines. I have a full row, and there's not going to be an ambiguous case here because we're not finding an angle. So this is just going to be a law of sines twice. Very fast problem, actually. So let's go ahead and do this. The tension sub 1 is to its sine of its opposite angle. As, let's see, the gravitational force, 278, is to the sine of its opposite angle, 63.8 degrees. That is, tension 1 is going to be the sine of 48.5 times 18,278. I'm going to type this in, 18,278. I've got to make sure I'm in the right mode on my calculator. Sine of 48.5, and then divide that by the sine of 63.8, and I get 15,257. We'll round that, 15 roughly, 15,257. That's how much weight this side of the cable should be rated for, because it's holding 15,000 whatever pounds. So it better be able to hold that. Tension 2 is going to be the same type of mathematics. So the tension 2 is going to be to the sine of its opposite angle, as again, that statement right there. So I'll go ahead and quickly maybe change, if I can change that, 67, delete 67.7. So I'll do that, 67.7. And this becomes 18,847, 18,847. Which brings up a really interesting point. So we're done with this problem. The tensions on both cables are known. There's almost 18,850 pounds of tension in this direction. Now, you might be wondering, how's there that much tension when the object doesn't weigh that much? The object doesn't weigh 18,800 pounds. It's 18,000, nearly 300 pounds. Well, it's because of the angle. If you've ever tried to hold something straight down, like at your side, it's different than holding it out at an angle. It's harder to hold something out at an angle. There's more effort being put into that. So it should make sense that there's more tension when there's an angle involved. So that's something I just needed to mention. But anyhow, these are the vector problems. They're really beautiful problems. You can really just do a ton of work with these. So anyhow, we're done with this video, and I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.